The Paws Pivot webinar series exists to support members of our community in Maryland, DC, and Virginia who've been impacted by recent changes at the federal level. These webinar series are a free educational resource for our community members to figure out how maybe they want to potentially upskill or figure out how they're going to pivot during this time of change and transition. So today's session is going to be on software, and Dr. Mohammad Samarah, who we have here, will be leading that. But next week, May 14th, we're going to have a session just like this on training to teach the next generation of pupils. So a lot of you may have 10, 20, 30 years of experience in what you do or what you did for the federal government. CTLS, our College Teaching and Learning Science program, might be an opportunity for you to figure out how to use all that specialized experience and imbue it on the next generation of teachers and learners. And after that, on the 21st, we're going to have a session on using the entrepreneurial mindset to solve problems and discover opportunities. So again, you've got all those years of experience that you had in your roles as a contractor or a federal worker, but potentially you can use it to your own benefits and starting your own, efforts or business. So those are the next upcoming sessions. You can feel free to scan the QR code right there at the bottom to sign up for those future sessions. And that'll be it for me. I'm going to go ahead and pass things off to Dr. Samarah, and thank you all again for being here.
Thank you, Rex. My name is Mohammad Samarah again. Delighted to be with you. Thank you all for taking the time to be with us. So let's get right into it. Today we want to talk about this thing we call software and give you a sense of its fundamentals, its anatomy, and why we think software is still eating the world and potentially software is becoming even more than that. So with that being said, I'm going to cover three things: the fundamentals of software and software engineering, demystify what software is and hopefully reveal its anatomy, and then try and predict the future, where we're heading with software and software engineering, and what it means to you and how you can take advantage of it. So software fundamentals. Well, first, where did software and software engineering come from? It turns out it came around the 1960s during our country's mission to place a person on the moon. This picture here, you see this young lady, a mathematician at the time, working at NASA with colleagues working on hardware, and she was in charge of the software that powered the landing vehicle to place astronauts on the moon. And that needed software and it needed programming. At that time, a little bit of a dark era in our history. Software was not seen as something men work on, so it was really pushed toward women. And so many female engineers and women engineers worked on software and mathematics. Margaret Hamilton is what you see in the picture here. She's a pioneer in this field, saw things differently and actually coined the term software engineering. And she's credited with the successful launch, I should say the successful landing on the moon due to her improvements to the software that's powering the landing vehicle. If it wasn't for her work, potentially that mission would have been a failure and potentially the world would have been completely different. So software came from sort of minority folks pushing the boundaries and asking for change, and that continues to be the case. There is some change and some hope, and we'll talk about that in a minute here. So if we fast forward, software is now, in these devices, these smart wearables. This is the device we give to children so their parents can be at peace. They know their whereabouts and they're able to communicate. If we look at this device, it has a lot of sensors, but what really makes it special is one thing, and that is software. Software is inside the device. It's in the interface. If the software fails, we call it a brick, and that means it has no value and no meaning. When I was going to college in the mid-'80s, late '80s, our vision of software and computing was these computers that you see here on the screen, this beautiful desktop from Apple and this portable computer from Compaq at the time. Our vision was you worked on that computer, you did what you needed to do in your office, at home, at your kitchen table, and then you closed it and went on about your work or life. That was a very limited vision. The truth of the matter is software is everywhere. Software is in your pocket, my pocket, it's in your purse, it's in our devices, it's in our physical objects. And there are many people in the world who are experiencing software for the first time through these smart devices. And every human on the planet is experiencing it, whether they are an infant, a 9-month-old, or people in their advanced age, in their 90s. So that means the game of software and software engineering has changed. And that means the knowledge, the basic knowledge and the basic fundamentals of software is not a luxury. It's not only for computer scientists, not just for software engineers. It's for anyone who lives on this planet. It's a human right. So, in other words, software is controlling all these systems and systems of systems that we have. And in order for us to create software in a meaningful way, we need to look at all the impact of that software on its users. So what do software engineers do? It turns out we see a problem, or we're told about a problem, and we come up with a solution. And then from that, we try to create and visualize some type of an architecture. And then we build and implement that architecture. But we're not done. Version 1 of any software product is the beginning. We have to evaluate how it works, how well it's working, and then adapt it and evolve it over time. If we look at what hardware engineers do, sort of a physical device or say an appliance, similarly, we see a problem, we conceive a solution, but here we create a product design. So that's a lot different than software. We create a product design, and once we're satisfied with that, we send it to manufacturing, oftentimes somewhere else or a third party. And then once it's in manufacturing, it's out, as we say, the cat is out of the bag, and the device and the product is in the hands of users. Now we start working on the next product. So that's a major difference. So in other words, software is almost like poetry, because it involves these programming languages, which there are quite a few of them. There are more than 50 programming languages that are in active use today. So you may ask, which one should I know? Which one should I be familiar with, or at least understand which end is up with? Well, it depends on what you're trying to do. So for example, if you're trying to do a web application, you may be using JavaScript. If we're creating, say, a machine learning application, you might be using Python or C and C++. If you're doing some type of AR, VR, it might be the Swift language that you're using. So it really depends on the product and the application that you're building. If we look at the ratings of programming languages, and this is as of yesterday, you can see Python is ranked top in terms of usage. This is an index that gets updated regularly based on a scientific survey. And you can see the other programming languages which have been here for a long time. C and C++ has been around since 70s and 80s. Java is circa 1995. You can also see programming languages like Pascal, which is, some would declare a relic of the past, but it's still in use. Most importantly, we see the structured query language, which powers queries and data retrieval from most of the databases in the world, is on this list. So let's pause for a second. And in many ways, this is the takeaway of this talk is, if I look at my phone, I have an iPhone mini here, I have more than 120 apps on it. You may have more or less. But if we look at all these apps and what they do, we can boil it down to these fundamentals, 4 fundamentals. So a computing device, an application, a computing machine only does 4 things. But we can combine these 4 things in infinite ways to create all the magic and all the joy and some of the agony that we have today with software. And so we came up with an acronym for it. So it's hopefully will become memorable. So, and you probably can guess what the C stands for. So we have to be able to compute. That could be adding numbers. That could be comparing 2 things. We have to be able to store things. In fact, these devices that are always with us, they're really just a memory machine. That's the killer application. It's not a phone anymore. Beyond that, it needs to interact with the environment. So it needs to sense the environment, take input from it, and produce output. That's it. That's all what a computing device does. And by virtue of extension, that's what software does. Every software application, every system in the world, regardless of how big it is, how much it costs, those are the fundamentals behind it. Software by itself is great, but software needs data. It's fueled by data. Software eats data for breakfast, lunch, and dinner, and even snacks on it after midnight. So it's important to understand data and how that is woven with software. So similarly, there are three fundamental concepts when it comes to data. We need to be able to capture attributes about a particular object, let's say its color, its size, its width, and so on. We need to be able to understand relationships between different objects, different entities. A car may have one engine or two engines. A car may have 4 doors or 5 doors, and so on and so forth. And we can create collections. These are data that are related to each other. From that, we can create multiple, more complex abstractions. This leads us to databases. So software needs data, and oftentimes the data is organized and collected inside databases. There are billions, if not trillions, of databases in the world. In fact, every device that we have has at least several databases on it. Your contact list is a database. Your browsing history is a database. Your photo library has a database, and so on and so forth. So databases come in different sizes, shapes, and scales. So it's important to understand the fundamentals of databases and what we do with it. Because oftentimes when we're creating a piece of software or using one, we need to understand how it's manipulating, how it's using, how it's monetizing our data. And some of that data needs to be held private and should not be monetized. So this is a common term that we use when we're teaching database management systems to students. Databases allow you to create new attributes or new collections, allows you to read them, update them, and delete them. So if you have an account, you can create a new account, you can update that account, you can retrieve the profile behind that account, and at some point, the account can be deleted. I thought it would be helpful just to kind of show you the different flavors of data, right? So this is a basic data file, comma, separated values, right? So it's a collection of what looks like contact information about the subscriber, right? And so if we zoom in here, we see the attribute. For example, customer ID, it's a alphanumeric value, first name, it's a proper first name, and so on. And it's all separated by a special character. And from that, we can take that further. So that's just one format, one flavor, if you like. We can also have other flavors, JSON and XML. JSON is the JavaScript object notation. XML is the extensible markup language. The detail is not important here, but it's what we see here is the same data, just represented differently. That different representation could make it easier to analyze, easier to store, faster to retrieve, and so on. Some of it might require more storage, more bandwidth, right? So for example, XML is what you see here. The extensible markup language is quite verbose, where JSON is somewhat a lot less verbose. But in real life, data is stored inside databases. And one type of database is called relational database management system. And it's very proper, very upright. Data is stored in a structured format. So what you see here is a proper database. This is a database schema. It has 3 tables. And this looks like a table. So the first table is country, second table is city, and the third table is country language. And what this represents countries in the world and the cities inside those countries and what languages are spoken in them. And from this database, we can ask 10 or 20 or 30 questions about countries that have not been perceived when we created this database. We can ask what countries in Asia have English as the official language. Period, right? So we can get a lot of insights because of the fundamentals behind this relational database is relational algebra. And so therefore it's very sound fundamentals. And so it's represented in tables and entities. And of course, this particular database is very small. In real life, a real database would have tens, if not hundreds of tables. I've seen systems with about 1,800 tables in them. So this is another example of a database. This has maybe about 20. It represents, I believe, a CRM type of application. And then what's important here is we can retrieve data quickly, and we can analyze, and we can slice and dice the data in many different ways. So if you recall, when I showed the programming languages ranking, SQL, a structured query language, was number 10. So it's an important aspect of what we do in software. So for example, here we can ask, give me a list of cities that have a country code that starts with an M, and only give me the top 20, right? Again, this question was not perceived by the person who built this database. I just came up with this question as an example, and you probably can come up with several others. So speaking of databases, so I said there are trillions of databases in the world. I probably have a dozen on me right now. But there are these pieces of software, we call it a database engine. Now, of those, there are about 500 or less. So those are like the Oracle database engine. This is the piece of software that allows you to store, manipulate, analyze, and execute the structured query language. So you can see Oracle is at the top here, MySQL, which is an open source database. We'll talk about open source in a moment here. But very importantly, this one on the bottom here, SQLite. That's a software library, about 3,000 lines of C code that fits on just about any device. It could be a nano device. And it's throughout the fabric of our lives. You have used it today, probably several times. And so this concept of database engine is not a foreign concept or something just computer scientists or software engineers talk about. So it's important to also understand the fundamentals of programming. It turns out there are really three important fundamental concepts: sequencing, I'll explain that in a second, branching, and looping. So we wanted to keep this high level, but we also wanted to show you some concrete things. So we can't really talk about software and not show you code. So, but we wanted to keep it high level, and hopefully this will come across. So this is a piece of software that allows you to take a list of numbers, whole numbers, integers, and sort them. A very basic approach called bubble sort. It works, but it's not very efficient. It works for a list of numbers that's small. So when we say sequencing, it means we're able to execute one instruction or one line at a time. So this is an example of that. Here we have this instruction which says we are going to create a memory location. We're going to give it this label I and place the value 0 in it. We're going to create another memory location, call it N, and inside that, we're going to store the length of that list that you asked me to sort. So let's say this is a list of 10 numbers, so N would be 10, and I would be 0. And from there, we can go on to the next instruction. So that's sequencing. When we execute this program, it runs very quickly, and it starts on this line here, and then goes on to the next line. And then it encounters other instructions. So when we say about branching here, branching allows us to say if there's a condition that's met, execute this code. If it's not met, execute some other code. So here we're comparing the value of this number against another number, and we say if this number is greater, then execute this code. Swap them, because this is how we sort. If the first number is 20 and the second number is 19, we want to bring 19 first. So we would swap them around. And we would keep doing that. This is where looping comes in, until there are no more swaps. And effectively, we have a sorted list. That's a very basic, a little bit of a naive approach to sorting. There are other techniques, of course. And we're still in search of a faster sorting algorithm. In fact, anyone who comes up with a faster sorting algorithm will make a huge impact and a difference in the world and potentially become very wealthy. The best sorting algorithm is called merge sort, but we won't have time to talk about it here. So that was part one. Hopefully that gave you an understanding of the fundamentals. Let's talk about the anatomy. Let's go down one layer. Really, we can't talk about the anatomy of software without talking about hardware, because hardware allows us to run and execute software. This is probably very familiar to most of us here. So the hardware has processors, memory, storage, networking, CPUs, GPUs, and so on. We won't spend too much time here. So software needs to run on an operating system. So it's important to understand the anatomy of the operating system. So in other words, when we're talking about software, there are multiple layers. And the operating system typically has a kernel, which is the core part of it. And then within that, the operating system needs to be able to connect to interfaces and devices. So it has a way to abstract the hardware, so we can keep adding new hardware without having to reinvent the operating system. And then within the operating system, we have these collections of code we call system libraries that allow us to do different things. And so together, these three components make up the operating system. So the operating system, like Windows, Mac OS X, iOS, Android, Linux, Unix, these are operating systems, allow us to execute software, right? So the program I showed you here, we can execute this program by asking the operating system to run this program. Okay, so from here, we want to look at the anatomy of a software system itself. And typically now we're dealing with what we said before. It's going to compute, it's going to store, it's going to do input and output. So in order to do that, it needs a presentation layer, which allows us to do user interface. We need to be able to solve the problem by having some type of a business layer, business domain logic. And then, of course, we need to deal with the data. And for that, we need to have a data access layer and then the actual data itself. So those are, generally speaking, the layers of a software system. And the user interface can vary. It can be a touch user interface. It can be spoken words. It can be a command line. It can be a variety of things. And we can have multiple presentation layers if we need to. It's important to talk about this concept of open source software and why it's important. So the Apache Software Foundation, which was founded about 26 years ago, is a pioneer in this space. The concept predated Apache, but Apache Software Foundation took it very far, is the idea to create software in the public and to be able to share it and collaborate on it across companies, across entities, across borders, and to have different models for the cost of the software, the access to it, the usage, the modification, and to ensure transparency. Open source software does not mean free cost, but it means different models for costs and access, modification, and usage. If we look at the Apache Software Foundation, their motto is software for the public good. So we want to make a difference. Public good does not mean we can't make money, but we start with meaning and then we make money after. It's incredible the success of this foundation. There are more than 300 open source initiatives. And I believe the number of collaborators is quite large, north of 80,000 collaborators. And there are a couple of 100 committees managing those projects. So these are active projects currently, and they range across databases to applications to libraries. Most of the things that we take for granted were innovations and initiatives powered by Apache Software Foundation or other similar open source collaborators. So that's something we emphasize when we teach software engineering. Let's take this one step further. So we talked about software system. Software system may have multiple applications in it. So it's important to look at the anatomy of a software application. So for that, there are three major areas, if you like: the code and the data, the architecture, which has all these layers that we talked about before, and potentially additional layers for integration and infrastructure, and then the supporting structures, the libraries, the frameworks, the operating system. In other words, when we create a software application, we're not creating everything from scratch, just like hardware. You know, this iPhone commanding $700 or more, it's not all made by Apple Inc. in Cupertino, California. The components are acquired from many sources, with a few that are, you know, exclusively made by Apple to differentiate it and to make it command this high price. Similarly with software. And that's really the holy grail of what we're trying to do with software reuse, and be able to use these components and libraries. That's why open source is a very important aspect of what we do, which lead us to this concept, software library. A library is just a collection of those functions, reusable code, like the one I showed you, this bubble sort. We can put that in a library and we can call it over and over again. Anytime you want to sort a list of numbers, you don't have to reinvent the wheel. Now we can compare bubble sort to merge sort to your sort, which we can claim that's faster, and we can test it and prove that to the world. So here's an example of a software library. This is the standard C library, and you can see these functions. These are functions that can be called and stitched together to make an application. Each function has its own specification, its own inputs and outputs, right? So for example here, this is a function that computes the absolute value of a number. It's pretty simple. It expects a number, a whole number, and it returns its absolute value. So if we give it -2, it returns 2. If we give it 2 plus 2, it returns +2. If we give it 0, it's going to return 0. If we give it a letter, it's going to return probably an error or an exception. So software is still eating the world. And if we look at kind of the evolution of things, we can see it. So I thought it would be helpful to share with you this particular device that I personally use and its evolution. This is a smartwatch tailor-made for running. So this is circa 2006. You can see this. This is Garmin Forerunner 305, I believe. This is the next evolution, 2009, 2019, and this is the current one, which I'm wearing right now. So how is that relevant to software? Well, there's software throughout this device. In fact, it has an operating system, an embedded real-time operating system that allows it to manage the sensors, the GPS radios, the Bluetooth radio and Wi-Fi radio, and so on, right? And you can see kind of the evolution in size and form factor. But what's important is that if we look at the features, for example, power source and battery life, the battery technology has not really changed drastically during this period. It's still based on lithium-ion battery. However, the amount of uptime without recharging has gone, and I can attest to this. This watch, in fact, in my experience, didn't even last 8 hours, can last 2 weeks. I often go a week and a half without charging. So that's slight improvement in hardware, but major significant improvements in software. So now this device has a power management subsystem on it, which is powered by software. Similarly, if we look at the display, the display resolution and density has increased considerably. That's because the software now is producing a lot more visual information and graphs and maps to the user. So the device evolution is driven by incremental hardware improvements, but vast software improvements. So I hope I have you intrigued, and maybe you want to learn the basics of a programming language. So for that, we actually have an 8-step method. We won't be able to go into the details of it here, but the idea is that if you want to learn, let's say, French, you have to understand basic vocabularies in a programming language that's called the data types. How do you describe a particular data item? Is it an integer? Is it a floating number? Is it a string? Is it an array? Is it a collection? Beyond that is also understanding the keywords. So for example, the C language only has 32 keywords, 32 vocabulary. It's the vocabulary list is 32 words, which is shocking, right? And then beyond that is to understand how to put all that together in these functions or methods, similar to what we did in the bubble sort. And then to take that further. To be an advanced user, you need to understand more about libraries and how to profile and debug and test your code, and special cases of usage that are particular to that programming language, sort of idioms. Just like in natural languages, we have all these terms and phrases that we say. Someone who's not familiar with it may not understand it. So the first four will take you from 0 to a beginner to intermediate, and then the last four will take you from intermediate to advanced and beyond. So I'm going to try and wrap up here. I know we're about at time. So this is my attempt at looking into the future, which can be interesting, but also a risky business. So we'll try our best to articulate what that looks like. Really, what we see is that software literacy is very critical for everyone, because now we have these physical objects that have software in them, what we call software-intensive products. So now software literacy is not, again, for computer scientists, it's a human right for all humans on this planet. And so basic software skills are as fundamental, if not more fundamental, than reading, writing, and algebra. So I want to leave you with a few resources. So these are some open source, open access textbooks that can be helpful in pursuing this further. These are some tools. We can't really give you tools and not mention Python, right? So there are a few tools there for Python. And there are other tools that you could use to look at other programming languages and look at data. Some data sources are important from the World Bank, US government's Open Data Initiative, and Kaggle data sets. Training, there are quite a lot of training out there. UMBC does have a training center, so I thought it would be helpful to give you some suggestions for things you potentially could pursue. Python, SQL, kind of looking at systems. And then lastly, and we'll finish here in a moment, what we see next is software becomes diverse and responsible, because we have diverse participation in software engineering. We are creating more and more responsible software, and software becomes a component of every economy. In other words, we want to go from software is eating the world to software is the world to we are software. And that's both exciting and can be concerning if we don't push this in the right direction. So in conclusion, we talked about fundamental software being compute, store, input, and output. Software is fueled by data. There are many promises and some challenges, but we must re-anchor what we're doing with software and say software must be ethical, reliable, and beautiful first. Thank you all for being here, and thank you for your patience. And with that, we conclude. I'll hand it over back to Rex.
Thank you so much, Dr. Samarah. That was a great and very informative session. I know it can feel like a lot, especially for those of us coming outside of the software engineering, bubble. But hopefully, today was an impactful and powerful insight into that world for everyone who was able to show up. On the screen, there's a QR code. It is for our exit survey. You can just hold your phone up to that, complete that survey, or you can click the link in the chat for the exit survey. The exit survey is very helpful for us. It lets us and informs us on what kinds of sessions you all need. We know that the impacts to the federal workforce and government contractors is something that's happening in real time. So the feedback on this survey lets us know where we need to pause and pivot and make sure that we're aligning what these webinars do with what you all need. So please, please, please take the time to fill those out. I want to thank you all for showing up today. And thank you again to Dr. Samarah for presenting. We know we're a little bit over time. We'll let you all get back to your afternoons. And we'll see you next Wednesday.
Thank you all.